Good evening. This is 6 o'clock. Let's get started. Before we start tonight's discussion on this digital logic gate design, especially focusing on the combinational circuit design, let me know if you have any questions or anything like that. Okay, so let's do a little problem, hands-on problem. Before that, let me just uh, share the poll for your general preparedness for this class. Please take a minute to answer this poll anonymously. Okay, I think most of you have done this polling, and let me share the result with you. With quite a lot of you, 45% has watched the videos for today's topic. Um, the other 4 students, please make sure you do that. Watch those videos, they're important. And the others are some of them, I hope you will catch up. Similar notes for the notes trend, we are seeing 61%. That's better for your class to have it done all the lecture notes. The others, please try to catch up. And apparently we don't have a question on the either on the discussion forum. I have checked. And okay, so let's do then this problem, and let's see if you have any question on that. So this problem is like this. Okay, so uh, here what we are trying to do is to design a digital logic circuit which will detect a 4-bit number. So that means our input side is a 4-bit, and let's say their input signals are W, X, Y, Z. Okay, and this W is basically represent the MSB of that number represented, the binary, and then uh, it will turn 1 if this 4-bit value represented is less than 3 or greater than 12 or divisible by 3. So if any of these condition meets, then the output is 1, otherwise 0. Now there is a restriction. We need to construct its logic circuit with the NAND only logic gates. We can assume multi-input NAND, that is like 2 or more input of the NAND gate that's available. So what you need to do is basically show the schematic diagram for the final logic circuit along with the steps to derive the logic equation and implemented circuit. So this type of problem, what we first step is to determine the truth table. So step one, construct truth table, right? So this problem, we see there are 4 bits. That means our truth table is going to be 16 row long, right? So let's construct that. So we have W, X, Y, Z. And let's, what is out? Is there anything out? Oh, yeah, out. This is my output. Okay. So, 8. Okay, then we construct the truth table 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and then 0, 1, 0, 0, 0, 1, 1, then 1, 0, 0, 0, 1, 0, 1. So this is the complete 16 combination of the WXYZ. And also let's note down their mean term. It will help us in constructing the output as well. So M1, M2, M3, M4, M5, M6, M7, M8, M9, M10, M11, M12, M13, M14, and M50. Now, we can clearly say if anything less than 3 or greater than 12, we can just make the output to 1. So 0, 1, 2 are definitely 1. And greater than 12, that means 13, 14, 15 are 1. Or they're divisible by 3. So definitely 3, like this, which is M3 or M6, M9 in this case, and M12. They're all divisible by 3, so I can put M3 as 1, M6 as 1, M9 as 1, and M12 as 1. So rest of the entries will become 0. Okay. Now from here, step 2 is write the SOP equation, which is in this case out equals sigma m of 0, 1, 2, 3, 6, 9, 12, 13, 14, 15. Okay. And next would become reduced Boolean expression. Use a K-map to do that. So this point, our K-map is going to be 4 by 4. WXYZ. Let's put the indices 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. This is a box of 0, 1, 2, 3, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So my, according to the SOP, then I can construct the this K table, K map as 1, 1, 1, 1, 1, 2, 3, 0, 1, 2, 3, 6, 9, 6, 9, 12, 13, 14, 15. Okay. Now we select the implicants, prime implicants, essential prime implicants. So I can have prime implicant like this, and another would be like this. Then I can have some alternate uh, let's say uh, like this, or I can have group like that as well. And for 9, 13, I can have either these or this one, right? So my list of prime implicants in this case is definitely 0, 1, 2, 3, and 12, 13, 14, 15. And then I have 2, 6, 6, 14. Then 9, 13, and 1, 9. Now out of them, these are the clear winner. They are essential prime implicant. So my EPI definitely is this one, and definitely I need to choose 9, 1 or 1, 9, because 1, 9 give you the least overlap, right? Otherwise, if we choose 13, uh, if we choose this guy 9, 13, it will have one unnecessary overlap with the group 12, 13, 14, 15. We can avoid that overlapping and have 1, 9. And then among 2, 6, 6, 4 is either way, like we choose it, we get one overlap. So let's say we choose 2, 6. Okay, so with that choosing of essential prime implicant, then we can actually claim my reduced expression is 0, 1, 2, 3, which is W bar X bar, or then it becomes like yeah, then it becomes the other one 12, 13, 14, 15, which is WX. Then about this one, right? 2, 6, we are making them 2, 6. For that 2, 6, it is W bar Y Z bar, and then for the M19, it will become, so 1 and 9, so it will become between these two group, it's X bar, Y bar, Z, X bar, Y bar, Z. Question so far?
Professor, why is choosing 9 and 13 any better than choosing 1 and 9?
Because 9 and 13, you're actually creating an overlap right here. So remember,
Isn't there an overlap in the first row if you choose 1 and 9?
Oh, you're right. Actually, it is overlapping with the with this thing as well. Yeah, yeah, you're right. You're right. So it is again then the random choice, basically.
Okay.
Okay. Yeah. Thank you very much for pointing that out. You're right. This is also overlapping with one. Yep. Okay. So now we did the first part, and now what we need to do is make a NAND only equation or expression out of this. Okay. So let's do that NAND only expression. So what expression I have? I have out equals so far uh, W bar X bar or WX or W bar X bar WX or W bar YZ bar W bar YZ bar or what was that? X bar Y bar Z, right? X bar Y bar Z. Okay, X bar Y bar Z. Right, this was our equation. W bar X bar WX, W bar X bar WX, W bar YZ bar, W bar YZ bar, X bar Y bar Z. Okay, uh, from here, what we can do, we can, okay, this is easy. This is easier. Like, let's, since there are no other constraint, we can actually write this, applying De Morgan, write this like this. Let's take this, each inner term, I am just inverting and doing and with using the using your De Morgan. So this is Wx whole bar, W bar Y, W bar Y, Z bar whole bar. That becomes one NAND, and X bar Y bar Z whole bar NAND. Okay, now you see like we have like we have NAND. This is one NAND. This is one NAND. This is one NAND. This is one NAND. The whole thing is another NAND, and it individual, each of this individual inversion, term inversion is NAND. And seems like we have inversion for all the term. We need W bar, we need X bar, we need Y bar, we need Z bar. So what, how we draw the schematic now is we start with W, X, Y, Z on the left hand side, presumably, and then make the inversion first. So this is like W bar, this is X bar, this is Y bar, and this one is Z bar. Now we construct the inner terms, the smaller terms. Okay, so which one is W bar X bar NAND? Okay, and WX NAND. So we have that NAND too. So we use another NAND there. And then we have W bar YZ bar, W bar.
Okay, W bar Y Z bar. We use three input NAND, and then we have X bar, Y bar, X bar, Y bar, Z. And then we do the NAND for all of them using a 4-terminal NAND. So this becomes my out. So this means like this is your entire circuit, logic circuit. As a black box, in-out schematic would look like this. W, X, Y, Z, their primary input and output is outputs. And this logical circuit performs this function, So if at the input side, let's say it came with, let's say 2, okay? 2 is like 0, 0, 1, 0. It should output become 1, okay? Now, if let's say at the input side, my combination is, let's say 5, right? 5 is 0, 1, 0, 1. My output should be 0, right? We can try it, like see if this works okay or not. So 0 means here is 0 and X is 1, Y is 0, Z is 1, right? So that means my W bar is 1, my Y bar is 1, and my X bar is 0, Z bar is 0. Okay, now look at this NAND. This NAND is fed with 1 and 0, which becomes like 0. And then let's see, 0, 1. And then the other one is, this one is NAND is 1, NAND is 0, which is coming from here. And another part is 1, 0, 1. Hey, 1, 0 is 1, 0. NAND is, oh my bad. This is 1. It is a NAND gate, right? So this part will become 1. And now about this gate, I see this is coming as 1. And this part is what? 1. And this one is Z, which is 0. That means at the end of the day, these become 1. And then this one is 0, which means I don't care about the other terminal. It's basically output will be 1. And that means this guy will become 0, right? The other part, like let's say, let's take through another testing. Let's say, similarly, if I have, okay. Now let's say at the input side, it came about 6, for example. Okay, input side 6, it came out 6. So 0, 1, 1, 0. And my expectation output is 1. So let's see that if that is the case. So my input side XY is 1. and W and Z is 0. So W bar will be 1, Z bar will be 1. And yes, any question? No.
Don't you need a fifth input for the constant?
For the one,
Yeah.
constant one, no, you can put it internal to that whole circuit. It's not an input.
Oh, okay.
Yeah, you are basically connecting that those pins directly with the VDD, which is kind of battery source or current source, you can say.
I have another question.
Yes.
Is the final NAND gate, I mean, is that just a shortcut of representing two NAND gates? We can write it like that, to combine all of the inputs for one output.
Oh, the four input NAND gate, yeah.
But in reality, it's broken down into two, right? Or is it all one?
It's broken down into, okay, this is a good question. So you can do like this, I think. So two input NAND is the fundamental logic gate, right? So you can do this way. Okay. Or you can do this way. Something like that. That's why VW. So either way, it's a four input NAND at the end of the day.
Thank you.
Okay, so let's get back to our quest. If these circuit gives correct result for this input, right? Let's try it. 1, then this becomes 0. This becomes 0. So at this point, this is 1. This is 0. So this is 1. Now for this NAND, this one is 1. This one is 1 too. So this is basically 0. Actually, I don't need to do other things, but let's do that. Like, since 1 is already as a 0, so I can expect it's the 1. But let's anyway evaluate the other part. For this NAND, my input is 1, 1, 1. Wonderful. So this becomes 0. This one, 0. And then for this guy, this is like a 0, 0, 0. This is 1. And your output is 1 in this case, which meets our expectation there. So this is more like a visual and manual testing. So that's another important step. This is schematic drawing, and other part. So this is like, and the other step is the testing. So we just complete the testing manually with a couple of patterns there and check that, okay, this is working fine. Question?
For the four input NAND gate that you drew on the right using fundamental logic gates.
Yeah, this is fundamental logic, right?
So
yeah.
It seems like there should be one more NAND gate to invert the output, right? Because right now it seems to be opposite of a 4 input NAND.
NAND. Oh, you mean this? Okay, let me revisit that one. Just hold on. So your AND is definitely like this. and is definitely like this, either this or this. Now, 4-input NAND is, let's say, X, Y, W, X, Y, Z whole bar, okay, is equals YZ whole bar by De Morgan, right? And then, so let's say this is like a T1, T2, both the terms. So this is like a T1, T2, and this becomes T1 bar, T2 bar, whole bar, okay, which is WX bar, whole bar, YZ. So this is one NAND gate. Do you agree so far, this conversion? This is one NAND gate. And then this becomes another NAND gate for inversion of that. And then this one would be another. So 4, 5. Yeah, you're right. Actually, we need a 5. 5 NAND for this one. So that means that let me just reconfigure this one. So this is two of them. Another two of them. Invert and NAND. Yep. At least on the very quick and dirty conversion, we can come up with this 5 NAND, and let us think later, like if we can optimize on top of that. Okay, we'll think later on that part. Maybe there is a scope to further optimization on this. Is that okay?
Yeah, that makes sense. Thank you.
Professor.
Yeah.
I mean, as a problem on like a quiz or a test, this seems like it would take a long time. I mean, how fast should we be doing this stuff? Like, how quick should we get at it, I guess?
As quick as possible. I don't know the exact like time, like I can tell you like you need to 1 minute, 2 minutes, 2 minutes, but it's as fast as possible. This conception needs to be clear for you.
Professor, how would we show a schematic drawing during the test?
Yeah, that's the problem. We in these format, online format, since Canvas doesn't have the drawing tools yet, so we probably would stop at this point. Like we just derive the formula and leave it there. Or problem can be other way, like given the circuit itself, now reverse engineer that. You know, like given this circuit, you need to come up with this guy, truth table. That can be another type of problem. Okay, what else? Let's see. Okay, we can take like about 5-minute break, and then we'll come back. Okay, let's get started after the break. So I want to show you something which is interesting but not useful in this semester, but it will be, you'll be dealing with that if you take 147 in with me, that course. So what I'm trying to do here is basically to show you an environment where we can actually uh, define this logic circuit, and test it, basically test and look at the behavior of this logic circuit, what is going to be. And that one is called and simulation environment, hardware simulation environment. And we use a specific tool called model sim. So model sim environment actually looks like this. This is a model sim environment. So you don't need to deal with that in this semester, like this course. This course doesn't is not about the Verilog, but it's in the 147. What I'm trying to say here, that when the hardware design or hardware engineers actually design a hardware module, they actually use this type of environment. This is, by the way, this is one of the like this tool is very widely used for the verification purpose, hardware design verification purpose, by the real hardware engineers in the industry. So this is the industry's one of the standard tool to actually test hardware circuits, at least the simulation, at least at the simulation level. So here in this circuit, one of the way we can actually start defining this hardware circuit as we drew here. So let's say I have this circuit has 4 input, 1 output, and that's what we are defining here, like a module. I'm trying to define, let's say, name it a my circuit module, and it has output and input. This we call a port, and then we are defining this port as WXYZ as an input port, like the design we had, and our output is the output port. Then what we need to do is basically instantiate, we call it instantiation, or start creating these NAND gates in the description. And what we see here, we have some, apart from the top level port, we have also intermediate wires, right? So we can actually define something like where, and let's say we call them W bar, X bar, Y bar, Z bar, and they took care of the, and then we need 4 more wires, seems like, to connect these. So we can just make it something like W1, W2, W3, W4, very simple thing. And then we just call, okay, NAND is, let's say, 0, 1, first instance. My output is W bar, input is W, and 1 bit. This is called 1 bit 1. Okay, 1 bit 1. So don't worry about the syntax and all this stuff. Like, this is fine. Like, you will be like dealing with that in the other course, but this is like something I want to brought you up to give you a sneak peek. This is X bar. Maybe, yeah, I need to change these. 3, 4, X bar, Y bar, Z bar, this is 4, X, Y, Z. So that took care of those 4, these 4 NANDs. Then I need to have other 4 NANDs, which is like, let's say we call them five, and let's say it is W1, which is NAND between W bar and X bar, right? I'm just looking at the schematic and trying to make that connection. Definitely, if we do a mistake here, we'll see a different result in my simulation output. NAND 6. The second NAND is WX. Okay, WX. Then the third NAND in that series would be, okay, W2, W3. W3 is basically 3 input coming from W bar Y Z, W bar Y Z, W bar Y Z bar, W bar Y Z bar, and then the other one, 6, 7, 8 would become my wire 4, and that is X bar Y bar Z, X bar Y bar Z, X bar Y bar Z. Okay. Now the last one, last NAND, this one is, it's a NAND is 9. Okay, my out is all NAND between W1, W2, W3, W4. Okay. So this becomes my description. So the pictorial description, the schematic diagram, we just described it in a language, and this language called Verilog language. Verilog language is, it is not a programming language. It's basically to describe hardware. It's a language to describe hardware components. Okay. So now what we can do here, we can actually drive this circuit, like remember, like in the example I was doing, driving this circuit. This is my in this case, this is my let's say this is what the MyCKT is. This is my MyCKT, and I need to drive this from the outside. So what we call here is called a test bench. Okay, where I'm instantiating my circuit, and from the outside world I am connecting some driver, which now we call that driver as a register. That's not important. And then we are probing the wire output, connecting to the wire. We are probing, we kind of probe that and see what's the outcome of this, and then we are connecting each of these output and input port of my circuit with this connection register, which is being driven by the values, and then outcome is probed with the wire out. And then we have some associate code, like don't worry what this code is, but it is basically cycling through the bit pattern, of all this combination, like 0001 to that 16 combination. So it is doing that part, and then what we can do, we can actually make it compile my project. Let's just make sure we compile it. This compilation is okay, and then we load the whole test environment, and let's throw it in the waveform viewing. So we'll be looking at the digital waveform coming out of this simulation, and then hit the simulation. So it's the end of the simulation, and then we can look at the waveforms. Let's see here. See your Z. Hey, why out is always like that? That's a problem. My circuit. Oh, typo. Use lowercase. Okay, let's redo that then. Compile, did it compile? Yeah. Reset. And run. Okay, now I have something. All right. So now look at these. Like this is your Z is a LSB, W is a MSB. So as expected, Z is toggling like between 0 and 1. Like if I hit this timeline, Z is 0, right? And then Z become 1. And Z become 1 here, Z becomes 0. So logically it is toggling. And we are seeing that MSB, most significant bit, is changing once, right? That is expected. Most significant bit in that sequence will change 1. So that means this point, it is representing this WXYZ representing 0, which expect my output expect to be 1, right? So it is happening there. Then at this time point, this entire digital waveform is representing 1, value 1 with WXYZ. Output is 1 expected. Then this one is, at this point, my input is 2, output is 1 expected. At this point, my input is 3, output is 1 expected. At this point, my input is 4, value 4, represent value 4, expected result is matched with the expected result 0. Same with the 5, then 6, it is 1, 7, it is 0, 8, it is 0, 9, it is 1, expected, 10, 0, 11, 0, and from 12 onward, it is 1. So seems like our circuit works. So this is how we basically, in the digital world, we use tools and use test bench, test pattern to try out the circuit description and want to make sure that whatever circuit we design is functioning as expected, at least at the logical level. One more side feature it has some debugging capabilities as well. Like we can look at some of the data flow. Maybe we can let me see. Can I do? Okay, yeah, to data flow. Okay, so this one, yeah. So let's see. Expand, unfold. Yes, see, we have exactly the similar circuit as we actually had, like 4 NAND from the primary input side, which is right here, another 4 NAND right here, and 4 input NAND finally here. So we can actually somewhat visualize this whole thing within this simulator environment, and also can debug. So we can actually inject the values and look at that how the value is logic value is traveling through the logic circuit, and observe if there is any problem that is causing any functional defect or anything like that. So anyway, so some interesting point I want to bring up today with you, and you will be dealing more with this specific environment, model sim environment, simulation environment, with describing hardwares in terms of Verilog languages in 147. Question. Okay, then if we don't have any question, then we can stop tonight little early, about 7, and we'll see you Wednesday, right? Yeah, Wednesday we have class. Good night,
Thank
all.
you, Professor.
Thank you.